Okay, hello and welcome to this YouTube tutorial on how to create a blood flow simulation completely from scratch using FFR data. If my voice is a little bit low, feel free to turn it up, but this will be a deformable constant simulation and not a steady, so just keep that in mind, and we're going to go from beginning all the way to the end. Let's get started. So the first thing you want to do is load up your 3D slicer and then find your data. We're going to be using number 2. I've already done number 2, but I'm just going to be doing it again just to show how it's done. The first thing you want to do is load your image and your label directly into 3D Slicer. Oh, there it goes. So you want to load that in to 3D Slicer. Your label is going to be segmentation and image will be volume. You hit OK, and you should see this. You click on the segment editor, make sure that segmentation is selected, volume is selected, hit show 3D. Click on the center view, then maximize view. This is the data that we're going to be working with. You want to make sure that there are no sharp edges. In our case, there is a little bit of one right there, but it should be no problem. Now we want to cut out the right artery, just like that. And you want to make sure that there's no like residual anything that's not connected, not unconnected to this. So it looks pretty clean to me, so it should be fine. Now this is ready to go to clipping. So hit next, and then export to files, STL, and then we're going to click and make sure it goes to the correct folder. In my case, it's in here, folder 2, and then you would click export. So I'm going to hit export. So here it is, label to segment, and this is where we're going to clip from. There is a case where the labels themselves will still retain the right artery. That will probably be a separate video on making sure that that does not follow through. For now, we're just focused on the simulation. So once you have that, you can close this up, and you're going to now boot up ParaView. Once in ParaView, you're going to load your segmentation that you just made and hit apply. Now you select it, click this little icon for clip with implicit function. Well, actually, no, slice with datasets with planes. I'm sorry. You click this one, and you're going to get greeted with this kind of box. You want to go to the properties, hit box, and make sure that inverted is deselected. Okay, I think I picked the wrong one. So then it must mean it's this one. Sorry about that. Yeah, it's the first one. I'm sorry. I'm probably gonna edit this out. But you click the first box, okay? Make sure that invert is deselected. Change this drop down to box, and then hit, before you hit apply, you're going to move this around, and you're essentially, what you're doing with clipping is you're removing all the ends of this artery. So after doing this for a very long time, I've kind of found some shortcuts, like using right click to quickly scale the box, using middle mouse button to drag the thing around, and then left click to rotate. Now, the trick to rotation is once you grab it and you put it close to where like you want it to be at, because ParaView does not have like the most optimal rotation, what you do is you select one side or any side, and let's say you want to make this go up. If you just bring it up, it's going to do that, and you don't want that, right? So if we're going back to where we were, how you do it is you clockwise rotate and then anti-clockwise rotate to really get it to where you want it to be. So if this is like down here and you just want to kind of move it up in this direction, you kind of have to rotate clockwise while you're going up, and then anti-clockwise like that to get it to where you actually want it to be. Once you have it in position, click and hold the top to kind of see where it's going to cut. The cut doesn't have to be perfect the first time, because you can always fix it. It's not like a clip is permanent. So once you hit clip, you'll see that. If you did not hit invert, what will happen is you'll see this. Don't panic, just hit invert and then click apply. You can always fix your clips even later on, so don't worry. Once you have that in place and you're done, you just rinse and repeat. Click the box again, set the drop to box, hit invert, right click, scale, move it around. Yes, it's a tedious process, but once you have it in place and you get more practice with it, you'll get much faster, and you put on some music and it'll feel like you're not even you're just floating. So yeah, you do that. That's another one. So I'm gonna stop talking now and just finish them. One thing to remember is they don't have to be perfect. They just have to kind of be perpendicular to the surface. You don't want something like this. That is not perpendicular. You want something that is circular in shape, so like that. If it's circular and kind of perpendicular to the surface, then you know you're doing a good job. Another thing to note is if you want to make sure that it's absolutely perpendicular, you can make sure that the top and the bottom of the box line up with the top and bottom of the artery. So right now, if I scale this down even further, you can see that it's not really lined up. So you can just, again, clockwise or anti-clockwise, maybe a little bit this way, maybe a little bit more that way, then hit apply, and now it's perfect. If you don't think it's perfect, again, you can fix it, rotate, and voila. So there's never any case where you need to stop and restart like I used to when I first started doing this. I would make one mistake and then restart the whole thing. Fun times. It looks perfect to me. Boom. Where it gets interesting is for the inlet. Um, the requirement is to keep as much, or ideally I should say, to keep as much of the artery as possible when it comes to the inlet, not so much the caps. So typically you would want to like line it up like this, where you take as little as possible off, and it doesn't have to be like circular in shape or anything like that. it just can't be like that. That is not good. This especially is a tricky one. So what I would do in this situation is this. So I would like line it up really close, rotate a little bit more. Yeah, this whole curvature is not something you would typically see, so it's okay to kind of get rid of it. But if you had something where it was like, ignore like this part, if you just had it round like here, you would line it up to where it's just like there, you know? Like you would line it up like somewhere there, wherever the opening you feel is. But for this one, we can kind of cheat and put it like right here. And drag this out, and then apply. This works. Well, you know, not perfect, but we don't have all day to really get it super duper perfect. If you want, you can take a little bit extra off, but I think this should be fine. Yeah, this will be fine. As long as it's mostly circular, for the most part, it's fine. Then here comes the interesting part. Once you're done, you click Filters, Alphabetical, and you want to hit Extract. I have it down, saved it on my favorites, but you want to hit Extract Surface. It's in bold. And just hit Apply. Don't think about it too much. And then this is optional, but you can do another filter. Go to Alphabetical and do Triangulate. Hit Apply. But the more you do this, you're going to want to save them into your favorites. Like that. Once you're done, hit Save. Go to your folder. I'm going to call this FFR2 clipped test just because it's for the video, but I would just name it clipped like what you see here. And you know you're saving it in the correct format as STL. If you don't extract surface and you hit save, you won't even get the option to save it as an STL. It would end up saving it as a scene file. So extracting the surface enables it so that you can save it as an STL, which is very important. So that's it. Now we're done clipping. Now we get to the interesting part. We boot up SimVascular. You want to create a new SV project. I've already created one. And there's nothing much to it, you know. You just give it a project name and then save it wherever you want to save it. Once it's saved, you can start to access it by just hitting File and then Open SV Project. You'll end up with this. The first step is to import the solid model that we just clipped. So you go to your folder, clipped. The naming convention is the model name followed by model. With FFR data, I like to put FFR first and then the model name or model number and then underscore model. So for some of my non-FFRs, I just have the number underscore model. No face found. Would you like to extract? You say yes. Keep the angle at 50. Global reinitialize. And most of the time you'll see some like residuals like this. You just want to delete them and only keep your wall. Now, I typically just label this artery and change the type to wall by clicking W on your keyboard or clicking here and doing that. Once you've done that, I highly recommend saving at every step. I'm not going to save just because this is a test run, but you want to save after everything because at any point it could crash. Okay, now that you've done the wall and you've saved, Um, my bad. To access this modeling thing, you click this button right here, SV modeling. Forgot to mention that. But once you're here, you want to hit fill holes with IDs, and you know you're doing it right when every hole that's been filled corresponds to something on the artery, meaning that it's not something that's like floating by itself. If you have anything that's floating by itself, go back, restart, and make sure that you cut appropriately and you clip appropriately and you smooth appropriately. Anyway, so that corresponds to something, that corresponds to something, that corresponds to something, that corresponds to something. Great. That's how we know we've done it correctly. So now you just click, cap, 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 whoops, and cap. You can name them. This is optional, but the naming convention that I like to have, just to make things simpler, is any arteries. So for example, this one is, let's see, this one right here is the left anterior descending LAD. So I just name it LAD. This one is LCX. I already know these, but I'm pretending not to for the tutorial. So just keep that in mind. Alright, then for the other ones, because there's so many possibilities of what these arteries could be, I came up with a simple naming convention where any of the arteries that are connected to the LCX that are facing the inside of the artery, facing towards or like facing inside, have the naming convention of M. So this would be M2 because M1 would be somewhere up here. This is like lower, so 2, and then if it's like any lower, it would be 3. Then this one is the D naming convention for diagonal, so we're going to name it D2. If it was any higher, I would name it D1. If it was any lower, I would name it D3. So, and then this one is the inlet. Yeah, that's the inlet. For reference, inside LAD is D, inside LCX is M. Outside LCX, I believe, is S, and outside LAD, which we rarely have any, but it's one of the letters. I forget. Probably N or something. If you name it N, I won't get mad at you. It's fine. Okay. You probably want to save after that. So you save, and then you're done with modeling. Now you click this logo right here, the yellow one, and you have access to the meshing. You right click the mesh, create mesh. Make sure that the correct model is selected. This is very important. Keep it on TEDGen and then name it FFR2 mesh. So similar naming convention, just name it mesh. All you have to do for meshing is click estimate, run mesher. Yes. And you'll know that the mesher is working correctly once some of these iterations start. And once it's done, it'll let you know whether or not it was done correctly. If it has problems, there's something wrong. Either you have like too sharp of an edge or something, and you may have to restart the process. If it works, then you're good to go. Alright, so If you were to do a simple mesh test just to see if you are free of errors before going through the entire clipping or modeling process, you would just upload the import the model and just go straight to the mesh part and just do that. So that's how you mesh things. Now, the final piece. We are at the simulation part. Now you just click the simulation button and right click, create simulation job, make sure that it's selected, call it FFR2, and then depending on the type of simulation you're doing, that's what the last part is going to be. We're not going to label it simulation, we're going to label it probably steady, if it's steady, or rigid. If it's a rigid simulation, you're going to call it steady, and then if it's a deformable, it's going to be deform, and then the type of deformable, which in this case is constant, so just const. Alright, now you're ready to simulate. For the initial pressure, a lot of these parameters can be subjective sometimes, but these are the best parameters that I've found. If you find something that works better than this, and you would like for that to be the norm, then probably we can look at that and make it the norm, but for right now, if you have it at 0, once you finish a simulation, you're going to end up with, I'll just show you. So if you started at 0, what's going to happen is it's going to simulate, 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 and then at 0, it's going to have a pressure of 0. So whatever you set that initial pressure to, when you run the simulation back, this is what it'll look like. It's only one frame, so you barely notice it. So it's really up to the simulator what they want to have at that step. To make it look nice, I will just go with the maximum. So I will go with 13, 1, 3, 3, 3, 3, 0, 0. So 3 threes, 2 zeros. Or you can even go with half of that, which is 6, 6, 7, 0, 0. We'll just go with 1, 3, 3, 3, 0, 0 for now. It may have some adverse effects, but I think this should be the way. If not, we're going to do 6, 6, 7, 0, 0. Let's go with this just to see. This should probably be the norm. Alright, now you go to your inlet outlet BCs. All you do is hit resistance for all the caps. So that's why it's important to name this as your inlet, because then you know. Or you can just hit R, 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 and then the prescribed values 1, 3, 3, 3, down arrow 1, 3, 3, 3, down arrow 1, 3, 3, 3, down arrow 1, 3, 3, 3. Now, for the inlet, it's a bit interesting. You want to hit prescribed values, set BC, and we're going to select a file called steady flow. Now, your steady flow file looks like this. All it is a text file with 0.0 space -65, enter 1.0 space -65. The website should have this file. If it doesn't, you can create it. It's really simple. Just a txt file with that in it. Pretty straightforward. But yeah, you're just going to select this file, hit OK. So now it is assigned. Next. So I already have a video on how to do rigid simulations, so this will be a deformable constant. For thickness, we're going to go 0.2. Elasticity modulus 4 million. So 1, 2, 3, 1, 2, 3. I'm going to keep these parameters the same. And then density will be 0.8 or 1. Then the pressure will be 1, 3, 3, 3, 0, 0. Now you're good to go to solver parameters. I have a file with the solver parameters in a Excel spreadsheet right here. This basically tells you what the solver parameters should be. So let's follow along. You can create your own Excel spreadsheet with this, but all you need to remember is these values and at these indices. So number of time steps, 150. This should actually be a 150. Oops. Yeah, that should be 150 because that just works best for deformables. Time step size 0.001. Number 5 will be 10. 11 will be 4. 17 will be 0.001. 23 will be 0.001. Then 0.01 for number 24. 25, 0.01. 26, 10. And 10. That's it. Probably hit save. Now, choose your mesh. Use MPI. The best MPI that I've found, I'm not going to go over the tutorial on how to do that, that's probably a separate video, is 10. But if you don't have access to MPI, you can just create the data files like that. That's probably simpler, and then you can just hit create files and then run simulation. But to speed up this video, I will set it to 10. That's the optimal one that I found. Create data files for simulation. Let it do its thing. Ignore all those warnings. It is taking longer because this is an FFR simulation. Some of the non-FFRs are usually a lot faster, but because FFR has a lot more data, a lot more quality, it just takes a little bit more time. So just hang in there. You'll know it's done when it no longer says creating data files, so let's just wait. Okay, it's done. Data files have been created. Great. From this point on, you can run simulation, and again, you don't need to use MPI for the first couple ones that you do, just so you get the hang of it. But once you get up to that point, hopefully I'll have a video on how to set up the MPI, but you can create the simulation files without it, you can run the simulation without MPI. So at this point, you would run simulation. Now, when I ran this FFR simulation, it took 16 hours. So we're not going to hang around for 16 hours. We're going to move on, but you would click run simulation. Okay? Click run simulation. Once it's done, it'll pop up over here. All you do is say start equals 0, stop 150, increment 10, and then you'll click convert. So now I'm going to go over to my actual SV project folder just to show you what that looks like. Let me close. So this is when I already have it complete, right? So I've already ran the simulation. This should show up. Don't click anything there, just 0, 150, 10, and hit convert, and then save it to the appropriate file folder. Again, I'm going to skip that. It usually doesn't take that long, but once you're done, wherever you saved it to, you go over, and you should see this. Lots of files, right? The only files you really need are the VTP files and the average result. So to show what a simulation actually looks like, we're going to go back to pair view, and you can choose to sort by type. That way it'll have all your VTP files. You select all of them from 0 to 150, paste it, apply, and now you should see your simulation. Some of them run forward, some of them run backwards. That's okay, it's no big deal. But you can iterate through them like this, and you can see the blood now filling, right? And then you can hit play just to play it. I hope you think it's as beautiful as I see it right now. Very, very good to look at. But that's just for visualization. As far as the data set is concerned, what we really need is the average result. So you paste the average result in there, apply, go to coloring and choose pressure average. This is the data that we're going to use inside the data set. And that's it. You will have completely successfully completed a simulation. Congratulations.